Okay, so good morning, everyone, and welcome to the Dionysos webinar. so, so today we will start for 2 hours about our digital twin project, and we will present you some of the results we got from this project. So thank you all for being here, and I will introduce our speaker today. So Adrien Hervoise from France Énergie Marine, he is from Brest. César Aguilera Esquivel from Cercel, who is located in Grenoble. Jérôme de Lauzon from Bureau Veritas. I believe, Jérôme, you are in Paris.
I am, yeah.
And Manuel Fernandez Perez from SciTech Bilbao. Okay, so we will go through some presentation, and at the end of the webinar, we will have some a Q&A session. So you are able to ask your question in the with this button here, Q&R, and we will try to answer all the questions. If we are out of time, we will take a bit of time later on to give you written answers. So first, let me introduce you a bit with the Dionysos project. So it is a project which started in December 2021. It is a France Énergie Marine project, so led by France Énergie Marine with several partners. I will not cite them all, but you can see their logos here. I will just use, okay. You can see the logo here, and it was financed by both private partners and public ones, plus French state fundings. So the objective of this 36-month project was to develop and test at sea a fatigue monitoring system for both floater and mooring lines of floating wind turbines. We choose to build a system based on a digital twin paradigm, and the idea is to use both numerical models and also sensors, and make the most out of both data, and this way try to improve the availability, to reduce the OPEX of the system, to get insights on the design models from ATI sensors to improve future designs, and also to anticipate possible lifetime extension thanks to a constant estimation of the residual lifetime with regard to real loads. There are several approaches we can have in such a digital twin system. You can think of a fully monitored structure when you rely only on sensors, and the feedback on that is that it is quite accurate, but reliability can be a bit difficult to get, because you are in a remote environment. Maintenance is difficult to be performed during 20, 30 years. So usually some sensors are working, some are not. And at the end of the day, when you add capex for the sensors plus the maintenance cost of all the system, it's quite expensive. The other approach would be to do fully numerical monitoring. But so it has many advantages in terms of installation and maintenance cost. It's almost it's not much. You can have a lot of redundancy with that, so you can be fairly reliable, but the accuracy, you don't really know how accurate you are if your model is not well calibrated over the time. So there is like a sweet spot we're trying to figure out. And the idea here is to combine both, to use some sensors to calibrate the model, to check its accuracy, and then the numerical modeling will bring a lot of reliability on the system, because when you have a sensor failure, you can replace your data with simulated ones. And the other advantage is that also you can have access to measurements that you are not able to do. Like, for instance, sometimes it's quite difficult to measure, I don't know, marine lines tensions, and in the model you have access to all the tension in the line. So, okay. So we first part of the project, we did build a software platform with the global architecture which is displayed here. And the idea that we gather and filter some environmental data, so wind, wave, currents, either from monitoring system or also from weather forecasts. Once we have the sensors data, we can force a global model, for example, OpenFast, but we can swap with any simulation software like CIMA or Kaflex or anything. We just need to write a bit of code to do so, of course, but the place is here to write the code. Okay. Once we force numerical models, we have some virtual sensors data coming, and on the other hand, we have sensors from the physical turbines, which can be compared with numerical sensors. So we gather everything in a unique place, a unique database, and then we can use a graphical interface to display information, to perform continuous monitoring, and track change in wind turbine behavior. So that's the overall idea. And we tested that software on 2 turbines. First, Zephyros wind turbine, which is a 2.3 megawatt turbine located in Norway. A quite special design, which is a spar, and another wind turbine floating, which is DEMOSAT, single point mooring turbine with 2 megawatt turbine on it. So DEMOSAT is located in BIMEP, and Zephyros is located offshore Norway. BIMEP is offshore Bilbao. Okay, so and today we will show you some results we got from the project on those 2 application cases. So first we will go through Zephyros floating wind turbine. César will present you the results we got from the modelization of the floater flexibility and the effect on the tower eigenfrequencies. On the same subject, Jérôme will show you how it works in their Opera software to model wind turbines. And then Adrien will present you some machine learning approaches to detect anomalies and to perform some regressions on the wind turbines. Then we will switch to DEMOSAT application case. Manuel will introduce the DEMOSAT system. And I will at the end present you the digital twin architecture we build on that and some model measure comparisons we have on an extensive dataset.